is joined to work with Ho-Jin Choi, who is a student of Sang-il and Sang-il and Paul Roland here. Okay, I think this is repeated many times, so I might skip. So class is chi-bounded if there is some function depending on the class C, such that the chromatic number is bounded by a function of omega. There are some interesting questions motivating me to work on the chi-boundedness. For instance, Charpak's conjecture says that, for instance, the class of graphs with no induced cycle of length and its k is chi-bounded. But recently, the Ska-Simmer and Szymanowski worked a lot on these questions, and then I found that recently Szymanowski, Ska-Simmer, Spocker proved that the last conjecture. Yeah. So in this talk, I'm interested in another operation instead of taking induced subgraph. So here we have a graph containment relation called the vertex-minor. To take a vertex-minor, you have one interesting operation called the local complementation. So when apply the local complementation, you fix a vertex, and then you look at the neighborhoods of this vertex, and then you take a complement of this neighborhood of a vertex. Then we say that this is an application of the local complementation at some vertex V. And for two graphs H and G, we say that H is a vertex-minor of G if H can be obtained from G by a sequence of applying local complementation and vertex deletions. Yeah, I understand that you didn't motivate much about the local complementation, so probably I need to give you some motivation. Actually, there is a really interesting point on the circle graphs. What is circle graphs? Circle graph is some graph classes where they have some intersection models on the circles, chords in a circle. So for instance, if you look at this left-hand graph, so there are 5 chords in the circle, and then they represent some vertex in the graph G. And two vertices are the adjacent if and only if their corresponding chords intersect here. And actually, you can observe that doing a local complementation at the circle graph actually can be realized in the certain operation in this code diagram. So I want to apply local complementation at vertex D. So how do I do? In this diagram is that this endpoints of D partitioned in the circle into 2 parts, right? And then I look at the right-hand part. The end vertices have some sequence, like here A and C and E. And then right-hand side, what I do is that I flip this sequence. You take a reverse sequence of this guy. You put the E, C, and A, and then you add corresponding. You connect the corresponding 2 endpoints. And then the resulting graph, you can easily see that the resulting new graph is actually the consequence of this applying local complementation vertex. Like previously, 2 chords looks like this, then this becomes like this, and then there were no edges, and then previously there was no edge, then this become an edge. And Bush actually characterized the exact 3 vertex-minor obstruction for circle graphs, and one of them is this Hill graph based on the cycle of length 5. So you can easily observe that you can draw a cycle of length 5 here, but you cannot draw a vertex dominating this cycle. Okay, also another motivation. Actually, I'm much working on the rank quiz. So rank quiz is some graph width parameter. I don't want to define exactly, but this is useful to dealing with dense graph classes. And Boucher didn't define the rank quiz at the moment, but Boucher actually observed that the function defining rank quiz preserved by doing local complementation. So the function is that you take adjacent, so you look at the vertex at S, and then you look at the complement of this S, and then you take a submatrix of the adjacency matrix. And then I want to local complementation V here. And then what I changed it in the matrix is that you look at the submatrix induced by the neighborhoods of V, right? And then you change it 1 to 0 and 0 to 1. But this can be considered as adding the row of V to the row of A and row of B. So this is elementary operation of the matrix, so rank doesn't change. So rank width actually doesn't change by local complementations. So there are some, we are expecting some structural theorem for rank width and vertex minor. For instance, if a graph has a sufficiently large rank width, you want to find some vertex minor in there or something like this. Okay, there are some interesting classes characterized by vertex minors, distance-area graphs and circle graphs. Circle graphs are obstruction set is this. And also, Sang-Yeon proved that graphs of rank width and most T can be characterized by finite list of obstructions. Interesting point is that all of these classes are chi-bounded. So Jarpaks proved that the circle graphs are chi-bounded, and quite recently, Drozak and Kral proved that the graphs of bounded rank width is chi-bounded. And Jim-Gyeonan conjectured that for any graph H, the class of graphs having no vertex minor isomorphic to H is chi-bounded. I think quite ambitious, but I still believe. No. Okay, what is known for this conjecture exactly? So in the paper by Drozak and Kral, they proved that the field 5 free vertex minor free graphs are chi-bounded. But this is already some application of the structure theorem by Jim-Gyeonan in his thesis. And then what I prove with is that if a graph is distance-area, then this graph can be obtained from some larger tree as a vertex minor. And then if you forbid the tree as a vertex minor, you forbid the all induced subdivision of the tree. So the scarce result about the induced subdivision of tree implies that if you forbid the distance-area, then you have a chi-bounded. Also, recently, Sudomsky, Skar-Simur proved that the class of no induced cycle of length n is k is chi-bounded, and this implies that the conjecture is true for cycles. So when I started to work on this is what I know, and then I want to extend slightly more graph than cycles. And then the first attempt was that the fan graphs, and actually we have a result with a Che and if you forbid the fan graph as a vertex minor, you have a chi-bounded. But actually, we were more interested into forbidding a large field graph because fan graph is a circle graph, so you forbid this, then the class doesn't contain all circle graphs. So somehow we want to generalize the result on circle graphs and result for the field 5 graphs. And then recently we proved that actually for every field graph, the class of graphs having no field as a vertex minor is chi-bounded. So this generalizes the chi-bounded property of circle graphs and field 5 vertex minor field graphs. So we have some time, so I would like to give some techniques to prove this. As usual, in many papers on the chi-boundedness result, so we use the leveling technique at the basic tool, as a basic tool. So you want to color by the graph, so you can look at the connected graph individually, right? So you can just color each connected component individually, so you can consider the only connected graph. And then you fix any vertex, and then you take a label from this vertex, meaning that let's say L of I is a set of all vertices of distance I from this fixed vertex. Then picture looks like this. And then simple observation is that each layer can be colored by some color peak colors. Then the whole thing can be colored by 2 peak colors by taking the even layers and the odd layers individually. So this implies that if the graph has a sufficiently large chromatic number, you should find some label which still have a large chromatic number. And then we use Shudonovsky and Skaden-Seymour's result on the induced cycle length n is k, so that we can assume that there is a very, very long induced cycles in this layer. And then we try to, starting from this configuration, we want to contract somehow the connected subgraph from the L1 to the LT-1 into the one vertex. Somehow strategy looks very fine, but there are many technical details here. Maybe before going to the technicalities, I want to give a short proof for the fan vertex-minor case. In that case, instead of starting with the cycle, we can start with a path to obtain a fan. So there are two ingredients there. So you start with some tree. L of t, you have some large induced path. And then look at the vertex adjacent, having a neighbors on the L of t. So if you have a vertex which have many neighbors on this path, then you just suddenly find the fan graph has vertex minor, because you can shrink a degree 2 vertex by doing local complementation and deleting the vertex. So we can assume that every vertex in the previous layer having a small number of bounded number of neighbors on the path. And then what I do is that, okay, I look at any vertex and then look at the neighbors. And then because path is sufficiently long and then you only have a small number of neighbors, so you have a very long subsequence which doesn't have neighbors on this guy, right? So you take a subpath which have exactly one vertex having a neighbors on this, and then you look at this subpath. And then we know that every guy in the L of t has a neighbors on the previous layer. So you choose another vertex, and then you look at the neighbors, and then you do the same thing again and again. So at each time you remove many things in the path, but still you can find some path, still large path with some kind of a matching structure. And then with some more argument, we can actually find some induced matching looks like this. Yeah, for really looks like this. You do some local complementation at here, but I want to skip this. And the other argument is that I want to forget everything in here, but I just keep that I take a union of the V from the L of t minus 2, which is connected. Because for each layer, we have some neighbor in the previous layer, and then we have neighbors on the previous layer, and then it's connected to the first vertex, right? So if you take a union of these guys, this become connected. So what I do is that I want to push a connected graph to the L of t minus 2 by doing this operation. So the local complementation have a law in here that you look at any vertex outside of L of t minus 2 and then look at the neighbor. If the neighbor is connected, then I just remove this. Then still this graph is connected, right? Because this vertex doesn't have a law to connecting, preserving the connectivities. But otherwise, if the neighbors induce this connected graph, then you do a local complementation here. Then we know that every graph is connected or complement is connected, so the neighbors become connected. So you do a local complementation and remove. Then preserving the connectedness of this graph, you can remove every vertex in the outside. And then you end up with some connected subgraph of L of t minus 2. And then you do some Ramsey argument on the connected graph, and then you can find some long induced paths. And then this is some special case, and then you can find a kind of field fan like this. Okay, yeah, somehow we can just follow the same technique for obtaining a field as a vertex minor. But there are some obstacles. The first obstacle was that so in the case of a path, if you remove the outside of a path, so you still have some subpath, which is path, right? But for cycles, if you remove some vertex, then you lose the information that this is a cycle, right? So we don't want to remove any vertices here. So this is a first obstacle, and then we want to exactly finding some subsequence which is really regularly adjacent to this cycle. So end up with some lemma, which we call the regular partition lemma. That okay, so I explained what it is. So you look at any real line, and then so each subset which we have here, AIs, is the set of integers in there where each set has a size exactly k. And then what I can do is that if this set is sufficiently many, you can find some subsequence of this guy, and then you can partition this original interval into k parts, such that if you look at each part, then this subsequence really looks like this. So, okay, so these guys are the corresponding integers, and actually, so these neighbors will be these integers. And then this is either appears consecutively like this, or all they have the same neighbors. So to obtain this, it's sufficient to apply the Erzos-Sekeres lemma for the first elements and second elements and third elements and so on. And then end up with some kind of this structure. And then briefly, the cycle have some at most k partitions where you have some subsequence, and this guy have either same neighbors on this part or some consecutive neighbors on the other part. So this is one thing that we have, and but the second obstacle was actually disturbing me at the first moment. And then last moment, you can find the graph looks like this. Like you have a cycle, and then you have some vertices. Looks like very regularly adjacent in the cycle, and then this guy adjacent to V. So I hope that we can find the real vertex minor from this. But we didn't prove that this doesn't contain the here as vertex minor explicitly, but we believe that it doesn't contain because I tried many times. But the natural attempt is that you do a local complementation at these middle guys to make edges from the V to the cycle, right? And then you look at looks like a cycle, but you create some many chords, right? If you try to delete some chords, then the cycle is removed, and then graphs is totally changed, so it's difficult to deal with this. So what we want to do is that we just simply avoid this situation that you want to find the two sets of such a structure where the one guys contribute to make edges from V to the cycle, and then the other guys to contribute to removing such a chords, created chords. And then for doing this, we want to have no edges between these two sets. Okay, so for this, we take multiple layering instead of directly obtain a cycle at the level with a large chromatic number, which means that you're starting from vertex, and then you take a leveling, and then you end up with some level with a large chromatic number. Then instead of fighting an induced cycle directly, you take another leveling from here. Because it has still large chromatic number, you can do this. And then you do this again and again. So this technique is already used in the many papers of Seymour and Scott, I guess. And then you don't need to really read about this. So what you end up is that you have a still large chromatic subset of a large chromatic number, and then you have a sequence of sets y1, z1, y2, z2, etc., where each guy has a neighbors on each yi, and then yi has a neighbor on the gi, and then gi has some root where for each vertex in the yi you can find some paths. Basically, you can obtain from here that the L of t minus 1 will be a y1, and then the union of other guys will be a z1. And then in the next layer, the second layer will be a y2, and then all of the other guys is z2. And then you can easily observe that the y2 union z2 will not have a neighbors on the z1. Like here, the y2 union z2 doesn't have a neighbor to the z1, but may have a neighbors on the y1. But we want to find the two sets yi and yj such that they have no neighbors on each other. So to do this, to find such two sets, we apply some Ramsey argument, which is already known. You just find many y's, and then we somehow give us some sequence on the yi, and then what can we simply say that you can find some clique of size k here, or you can find some large subpart which have no edges in here. But actually, you don't need a 3-layer. It's sufficient to have 2 layers in our applications. And then what they actually need is something like this. So you have some graph of large chromatic number, and you find the induced cycle here now. And then you have 2 sets, yn, yi, yj, which have no edges between them, and then each yi also doesn't contain any edges. And then you don't actually need a gj, because you just need to gi, which have these guys one to adjacent to this cycle. And then now we applied the regular partition lemma to the yi once and then yj once. If you apply the regular partition lemma to yi for the neighbors here, so I mean that you just you cut some error and then you look at this as a real line, and then you apply the regular partition lemma. Then the lemma implies that you have some partition of at most k parts, such that each part, the neighbors of yi, appears very regularly. And then you choose one non-trivial part, and then inside of this line, you apply the regular partition lemma for yj. And then if you look at this part, then yi and the yj altogether have very nicely connected. And then using this structure, we can find some smaller, there are many special cases, and then we can reduce to the smaller graphs to obtain some small graphs. Maybe I can give some small example where actually, so it's not sufficient to look at here because sometimes it doesn't create the field vertex minor. So from yi, so there are some another parts which is also useful. So we can take this guy and then this part. So then we can look at you have one interval where these two sets are both connected to regularly somehow. And the other part is only one set is regularly connected. Because for the second set, I just take a regular partition lemma for these smaller parts. So we only know the information here, but we don't know the information between yj and then this another part. But we can argue that whatever this guy is adjacent to this guys, so we can find the field as a vertex minor. Like maybe so this guy has some neighbors on the gj, and then maybe this guy doesn't have any neighbors here, then probably I just use this cycle as a base cycle, and then you can contract this to make a field as a vertex minor. Or maybe this guy is regularly connected, then you can reduce kind of ladder graph here to find the vertex minor, field vertex minor. Okay, so this is all. And so we are happy because I was interested in the field vertex minor graphs at the first moment. But for general question, I don't know what is the next attempt. So maybe we can try, looks like this. But I just want to remark that so if every graph actually can be obtained from the large grid as a vertex minor. So this is a very interesting observation. So it's sufficient to prove for the grid graph. But I don't know whether this is helpful or not. Okay, I also want to remark that Sang-il proved conjecture that for every bipartite circle graph H, the class of graphs we know H vertex minor has bounded rank with, and there are not much result on this. Even actually, we don't know when H is some path of length 8 or something like this. So probably, maybe you can try for doing this conjecture. Thank you.
All right, are there any questions?
Yep.
Jim?
2 questions. So in the conjecture of Sang-il's,
Yep.
why is bipartite?
I don't know. So the conjecture was for people minor actually, it's written in there. Yes. And then probably for vertex minor, maybe bipartite graph. Yeah, maybe only circle graph. Yeah.
My second question is related to that. So fan is a circle graph.
Then it's circle graph, yes.
So it should have bounded rank like things they exclude, things with no fan.
If you exclude the fan as a vertex minor,
It should have bounded rank.
I think so. Yeah. But even for cycle, we don't know. Yeah, because cycle is obtained from fan graph, right? But even if you exclude the cycle, I don't know whether it's a bounded rank. Yeah, maybe it's good to attempt. Yeah.
Are there any other questions? Okay.